expected of you, is right? So I'm going to do some problems today based on this transistor stuff, and then I'll answer questions that you have in general about the final exam and anything like that. Remember, the final is comprehensive, but if you know one thing about this course, you can't do power problems unless you know Ohm's law and how to do basic circuit analysis. So most of the course builds on everything that's been done, the exception of transient problems. There'll be one transient problem on the final. I'll get through this and give you an overview. But in general, if you've been keeping up, you're probably in great shape right now because it all builds. There's not a discrete, set of material that's not unrelated to past material. All the things based on circuit analysis. All right, so about the examples of the problems that didn't boast. They're actually quite easy, but I want to go through them. So it starts with 1141, and you don't have that unless you have this book, which I think some of you actually do. Put the number up as a reference. So for 1141,
You ready to cry?
it has So here's sort of a typical, very basic problem based on what we covered last time. This is a transistor, it's an NPN. This is the emitter, that's the base, and that's the collector. Here we have a current called IC, it's I collector. We have a current here called I base, these are all DC currents. And we have a current here called I emitter. The relationship, it's obvious just looking at that, IC plus IB has to be IE. So you could say that IE is equal to IB plus IC. The other relationship is that IC over IB is beta forward. Those are the two relationships you need for this. And one last thing, for current to flow in this is the base to emitter voltage. And this voltage has to be 0.6 of a volt. I'm going to show you how you do these problems. The way you do it. You always look at the current in the base. That's what you need. That dictates everything. So when I want the current in the base, I want you to follow me on this. That current in the base, well, the voltage here is 2 volts is driving it, right? You all see that, class? Right? 2 volts. But there is 0.6 of a volt drop here. That was given right there. Most of the time with transistors, and the ones you see on the final, would be 0.7. All right, that's what I'll give you. But here, for some reason, he's chosen 0.6, probably just to throw you a curveball. So now you have to say that the total voltage driving current this way would be 2 minus 0.6, and the thing that limits currents is the 50K ohm resistor. You all see this, class? 50K, right? So I divide it by 50K. By the way, your phone was in the main office. Did you get it? I'm sorry about that. And you're going to get a value for this. If you have a calculator, you can give me that value. It's small. It's maybe of the order of tens of microamps, but you can just do that. 2 minus 0.6 is 1.4 over 50K. It's like 2.8 over 100K, so it's about 2.8 times 10 to the minus 5th, isn't it? Am I wrong? Anybody doing this problem?
Right. Yeah.
2.8 times 10 to the minus 5th? that's how much current is in the base. Automatically, how much current is flowing in the collector? Just look at that. Well, 100 times as much, right? Because I collector is the forward gain beta, which is 100 times I base. If I base is 2.8 times 10 to the minus fifth times 100 would be 2.8 times 10 to the minus third, or 2.8 milliamps. Do you agree with me? This is just to get you familiar with that. Everybody agree? That's it. That's how you do this problem. Now, again, this is a very uncomplicated circuit on purpose. You always start with the most basics, then you build complexity into it. So when you analyze it, you'll understand all the things that can happen. I'm about to change this a little. Ready? And now here's the next bit. Yes?
5 volt doesn't factor into that at all?
That's the thing you're supposed to see. The voltage there doesn't do a thing at all for the current. It's all determined by the base current. But I have to be careful about this, because if it was self-biasing and I pulled the resistor down here to here without having that, then that voltage does play a bit of a role. But it's only the base current ultimately that matters. Does everybody understand that? Only the current through the base. This is called a current-controlled current amplifier. Now, something I'll say, this voltage here, you have to have at least 0.1 volts from here to here for this to be in the active region. I'm not going to ask you about this, nor am I going to try to trick you on it. Remember, with these transistors, they can work in what's called the saturated mode or the active mode. This is active, where you get a linear amplification. Whatever current there, it's 100 times that there, if it's in a linear range, and that's what kind of problems you're going to get. Now I'm going to go on to the next part of this problem. I'm going to springboard off of this one. Please watch. We're going to do a new problem using this with one change. Now I'm going to put a resistor here. And I'm going to make that resistor 1,000 ohms. All right, just listen. Yeah?
What's the writing say next to the 0.6?
That's just four junction bias. It's the on voltage. I called it the on voltage. It's how much you have to have before current will flow in that transistor. If, for instance, if this voltage was 0.2 volts, nothing would happen. 0.3, nothing would happen. Got me? It has to go to at least you have to have this voltage there. Yeah.
You said that's usually 0.7.
Yep.
Are to assume that it's 0.7 if it's not otherwise?
I will, yeah, and for any silicon technology, the on voltage is giving us about 0.7 volts. Now, at extreme temperatures, super low, super high, it's going to vary somewhat. But in room temperature, for most applications, it's 0.7 volts. I've been doing this stuff all my life, it seems like. I've never done a transistor design without that assumption if it's silicon. Now, gallium arsenide, gallium nitride, gallium arsenic, silicon carbide, those are different compounds. That voltage will change. But for, as a matter of fact, for gallium arsenide, it's much less. It's like 2 something, I think, volts. So you have to understand this is for silicon, but that's the dominant technology that's used for everything. All your computers and stuff are based on VLSI circuits that are created from a large piece of silicon, really crystalline silicon that's done. Have you all seen this ever, where they take a piece that they create silicon in large, I call them ballonis. They're about 5-inch diameters, and they slice it with a diamond saw or laser saw to super thin things. It's crystalline silicon. Then they create maybe 1 million transistors when they do lithography on it and diffusion. Anybody ever seen this before? Nobody. Well, believe me, you're going to be every single one of your devices there, from phone, computer, your Google Watches and stuff. They're all based on that. Yeah.
So just to recap, make sure I fully understand what you're saying. So as long as that voltage and the ID is over 0.6,
As long as you can get at least this voltage that's on, right?
Yeah, as long as it's at least 0.6.
Right. As a matter of fact, let me just say this, because he's brought this up. If you were to put, now don't change anything in your problem. If I put, since it's 0.6, if I put 0.601 volts there, all right, then still all 6/10 would be driven across there, and only the 0.001 volts would be left to cause current to flow. Do you follow me on that? That's the way you think about these. That's not exactly true, but it's a close approximation to the truth. All right, now, I put that resistor in, and I'm gonna leave this as 2 volts, alright? But now I want a different piece of information. I want this voltage between the collector and the emitter. Everybody with me? It's just one incremental bit different. So first thing is, does IB change when I put that resistor in? Class? How many thinks it's the same? How many think it's different? It's the same. It has to be, because that voltage doesn't have anything to do with this current. Alright, so yes, IB is the same. If IB is the same as I see this thing, yes, at least it's in the active region. I'm not going to give you one not in the active region. So if IC is the same, then what is the difference? What do I need to do to get this? What would the voltage between the collector and the emitter be? Well, what would it be? I have 5 volts here, right? Before it was 5 volts, wasn't it? But what's reducing it? This voltage drop, right? Correct? So if VCE would be 5 volts minus IC times RC, that's the resistor is termed RC. Or it's really going to be 5 minus 2.8 milliamps, right, times 1,000. Or that's 5 minus 2.8, correct? Or it's what, 2.2 volts, isn't it, class? You with me on this? You follow me, just a little bit different, right? I'm gonna go a step further. I wanna keep springboarding off this one if I can. Ready? This is different. I want you to pay attention. Now for this purposes, I'm gonna get rid of this resistor. That resistor's gone, but I'm gonna do something else. I want you to watch. I'm going to go ahead and put a resistor between the emitter and ground. You can call that ground. And make this 50 ohms, all right? I'm only making it 50 ohms. Now please watch this. This is different, but you have the tools to do it. Now there still has to be 0.6 of a volt drop there. Follow me? But I want you to please watch this. Remember, the key is getting the current in the base, bless you, this circuit, correct, class? If I want that current, well, I've got 2 volts driving. I'm going to just put it down. I want I base. That's what I'm after. So here's what I'm going to do this time so you can see it. I'm going to go around this loop and take the voltage drops and set it equal to 0 so you can see it exactly. Are you with me, class? Remember, this is plus to minus. Right there, 0.6 volts. So I'm going to go around there this time, the first time. Then you'll see how to deal with it. If I start at ground and I go up, I get an increase of 2 volts, right? Then I get a decrease of 50K times IB. Does everybody see this? It's minus 50K times IB. You don't know what IB is. Then it's going to be minus 0.6. Does everybody see that, class? You guys good with it? So it's minus 0.6. Then from here to here, it's going to be minus, not IB, but IE. Follow me. IE times 50. So it's minus 50 ohms. I just put 50 times. Now, that's IE. All this equals 0. You agree with me? Short answer. I do this on purpose because sometimes I thought I was clear, but I wasn't. And if I know I wasn't clear, I'll try to come back and correct it. Everybody got that? Now, the next thing, and you kind of know me, I'm going to take that 2 to the other side. Does that make sense? What am I going to do after that? So this becomes minus 2. You know me, you'll know. Anybody?
Get rid of the negatives.
Get rid of them negatives. Nobody hates negatives like I hate negatives. One other thing I should have done. Can I take that to the other side? So now this is going to become negative, right? On this side? I'll leave it that way. I'll say 2 minus 0.6. I won't even do the calculation so you know exactly what I've done. Agreed? Now this is the part you have to make sure you see. Now IE is this. Or IE is equal to IB plus IC, but IC is beta forward, right? times IB. Or I can say that IE, and I'll get out of your way, is equal to 1 plus beta forward times IB. Everybody see that? All right? Now when I do this, I can say that I have 50K times IB plus 50, but now my IE is going to be 1 plus beta forward, I'm leaving it this way intentionally, times IB is equal to 2 minus 0.6. Does everybody see what I've done? Again, I'm solving for IB because that controls everything. Y'all see this? If you have a question, just ask it. I'm more than willing to entertain questions. All right, so what do I need to get IB? Now I say that IB here is equal to 2 minus 0.6 over 50K, that's that, plus 50, just 50 times 1 plus beta forward, and that would be IB. You'll notice that beta forward is 100. Well, 100 and 101 are pretty darn close. My rule of thumb is anything over 100, beta plus 1 is about beta. I just put 100 there. That's me. You're not going to see a big difference, trust me on that one. So when I do that, what is the value going to be? Well, that would be 1.4, correct? And what happens downstairs? I got 50K plus this, so I have, make that just 100. So I have 50K plus, well, 50 times 100 is really plus 5K, isn't it? Isn't that? If you make this just 100 times 50, right? Isn't that 5,000? Got me on that, class? So when I look at this, it's 1.4 over 55K. And what is that in terms of IB? I'm trying to show you something. Can somebody give that to me? I know you guys got calculators. And I appreciate it. I'm trying to prove a point here. That emitter resistor is small, 50 ohms, relative to the others in the circuit, right? But it has a tremendous controlling effect. What's the current now?
2.54 times 10 to the negative 5.
2.54 times 10 to the minus 5 amps. You'll notice before it was 2.8 before I put that emitter resistor in. What happens is the emitter resistor effectively limits, or it effectively is going to be something that in the future is going to be used. Well, it has a lot to do with biasing and stuff like this, what's called the key point. But the thing about this is, when seen from a base circuit, it's magnified by beta. I'm going to give you a general equation in a second for this, but I want you to see it. How many see what went on there, right? And the key was writing IE in terms of IB. That was the key to solving this problem. This is a common problem, all right, this type of thing. Now, something I'm going to say right here and now, because I'm trying to add some information. We're doing DC biasing, right? What you're going to see in some of the problems is this. You're going to see a capacitor here. That has to do with AC phenomena, and a capacitor here. What does a capacitor look like at DC? Open circuits, so you ignore them. All capacitors you ignore when you do these DC biasing. Does everybody understand that? Now they're there for AC, and here's why, just to give you a peek. These capacitors for million frequencies will look like short circuits. They're designed that way. So that means all the AC signal from here is the same as here, and it has to do with amplifiers. They need this, though, right there, for self-biasing and also for stability. And I can't get into all that in this lecture, but just realize you're going to see circuits like this. In your lifetime, you probably will be dealing with all sorts of circuits that have resistors there. Anybody here doing anything with drone technology or with any completely autonomous vehicles, anything like that? Not yet? Are you going into it, anyone? That's a hot area. I mean, the Tesla car and stuff, the Google stuff, is just the beginning. You're going to have all sorts of stuff where they're going to be using this type of technology for power amplification. And I'm going to tell you that you'll see it and see it and see it and see it until you're sick of it, but they're going to use it. Now, I'm going to do this so you'll see it. Write this down just as a template so you understand. in general, if you have a voltage here, plus or minus, and I'm gonna call that VBB. You can call it what you want. This is gonna be R sub base. I'm only gonna give you NPNs, that means the arrow's pointing out. Generally, I like to put a circle around it, the book doesn't, that's a transistor. If you have this, and you have RE here, and this is the emitter, the base, and the collector, and you have some resistor here, it's RC or R collector, and then you have a voltage here. Almost always, that voltage is termed VCC. It's the voltage that's driving the collector. I'm going to show you the equations for this in general form. I'll try to be clear about this thing. That's VCC. This transistor is going to have some beta forward, whatever it is, and we'll assume that it's got some VBE on voltage, all right? So this is wide open. I've not nailed anything down here. And what I want to do is two things. Well, actually, three things. I want to find I base. I want to find I collector, and I want this. The voltage between the collector and emitter. That's almost always something that's asked for. Everybody got that? Current in the collector, current in the base, and and voltage across the collector to emitter. Do you all see this, class? All right. Now, first, you got to get the base current, and I'm going to explain this. Last time, I wrote a loop equation here, right? But ultimately, I knew one thing, that the net voltage that's driving current this way is caused by VB. You all agree? So it's that voltage, but I have to subtract the VBE to get the net voltage that's driving current around. So I put VBB minus V base to emitter, whatever that is. That's usually 0.6 to 0.7 volts. For me, it'll be 0.7. Then I divide it by something. Well, what limits the current? Well, one thing that limits current is RB. It directly limits current. It's the base the resistance to the base of the transistor. But this resistor does too. But remember what you just learned. The effects of this resistor, because it's times the emitter current for the voltage drop, and the emitter current is beta plus 1 times the base current, correct? What you end up doing is you have plus 1 plus beta forward times RE, limiting that current. Thing to take away from this is now the emitter resistor is amplified by 1 plus base, or 1 plus the forward beta gain, the forward gain of the transistor, and that's how it's felt in the base circuit. Does this make sense to everybody what I'm doing here? So that limits the current. Now that's the actual base current. Collector current is simply equal to beta forward times I base. You get that just by knowing that relationship. Finally, to get the voltage across the collector and emitter, how do I do that? All right, let's talk about what's the maximum it possibly could be if there were no resistors there and there. Class? VCC, right? Whatever that voltage is, that's as much voltage as there available between the collector and emitter, correct? So you put down VCC first. What reduces the amount of voltage here? The voltage drop here and the voltage drop here. Do you agree with me, everyone? So it's less that. So now you say it's that minus IC times RC minus IE times RE. Y'all with me on this, class? Now I can, you got a question? I can write this in terms of just the base current, can't I? I can go ahead and I can say that now voltage collector to emitter is equal to VCC, whatever that is, minus, well, IC is just beta forward, right? Times IB times RC minus an IE is beta forward plus 1 times IB times RE. And if you want to, you can manipulate this some more and just get IB by itself and all the other terms inside that. You all see this, class? And that's how you get the voltage collector to emitter. Now that can never be negative. If you get a negative voltage, either the problem was messed up by me or it's wrong. So there's a calculation you've done wrong. You follow me? Because these drops will always be less than VCC. Got me? All right, that's how to do that problem. And I gave you a general formula to apply. Now I want to do one based on self-biasing, and I'm going to do one that I did last time with different values we're going to calculate. I'm going to do two different problems here. We got some time. Yeah.
When you do the 1 plus BF for the IB equation right above you, and you multiply it by RT, on the previous problem, the 1 plus BF is multiplied by IB.
Right. But I mean, what did I actually do there? I was solving for IB, wasn't I? Look, so the problem before that, I wasn't solving for IB directly. I wrote a current equation, right? And then we had to separate it out to solve for IB. See, IB times RB is the voltage drop in the base circuit. IB times 1 plus beta is the current IE. That times RE is the voltage drop on that resistor. But if you're solving for IB, you wouldn't have IB on both sides of the equation. Yeah.
Is there any way to have a situation where if you have more than one voltage source and you know that one of them is going to be less than the forward bias voltage, which you just not considered? Does that ever happen?
I think you're possibly thinking about something that could be too tricky. I'm not going to try to trick things. They're going to be straightforward things. All right, now this problem, I want to see how you would do it actually. For the record, this is 1152. And here, VBE, as in most cases, is 0.7 volts. That's what it should be. Beta forward is equal to 200. That's more common. And they have this. They have 9K and then 3K. They have a transistor. They have 5K. They have 2K. And they want to know what this voltage is. They want to know, I want to know what this base current is, and I want to know the collector current. All right, so how do we do this problem? Last time I went over it, unfortunately, the homework didn't post. But do you remember how to do this kind of a problem? I'm not going to call on you, but how many do? All right, some of you, not many. The trick is what? With this part of the circuit, we're going to make a Thevenin equivalent, right? So I'm going to break that right there. And I'm going to say what I'm going to do is create a Thevenin equivalent for this part of the circuit. So if you look at that, I'm going to just break it out by itself. I have, I'm sorry I didn't put this here, this is 10 volts. So I have this, I have 10 volts here. I have 9K, and then I have 3K. That's grounded. And here's my output terminals that I'm going to hook something up to. So I want a Thevenin equivalent for that part of the circuit. This is going to be plus to minus V out. In this case, when there's nothing connected, it's called V open circuit, isn't it? Right? Think about this. This is a Thevenin circuit, right? We're going to connect this stuff to it. But to get the Thevenin circuit, we first disconnect the load. Do you remember that? You identify the load, then you take it out. That was the first step for Thevenin analysis. Do y'all remember that? Second step was what? Finding the open circuit voltage. Well, how much voltage is here? Just look at it. I got 10 up there, right? So it's 10 times what? Times the resistance we want the voltage across over the sum of the two, right? You all agree with that, class? That's simple voltage division, isn't it? We've done that all whole semester, basically. Well, what's that going to be? That's 1/4 times 10, or 2.5 volts, isn't it, class? Right? That's the open circuit voltage there. Y'all with me? What's next? What's the next thing I do when I'm doing a Thevenin equivalent, guys? Did you find a vowel meant to talk to me? What is it? Say it. Say it again.
Turn off the sources?
Yeah, sort of, kind of, but what's that word that I'm looking for? The Thevenin resistance, right? I'm looking for the resistance. So I turn off the sources, which means that goes to ground. You with me on that? If you make 10 volts 0 volts, it's effectively a ground, isn't it, class? So what's the resistance between those two terminals? Isn't it 9 in parallel with 3? All right, so come on, you can see that, right? These two are the same points. These two are the same points. They're parallel, right? Just look, same voltage between them, right? Put 2 volts there, from here to here. The plus is here. That's ground, right? Everybody see that? So they're in parallel. So it's 9 in parallel with 3, or really, what is that? 27 by 12, right? Okay, and I don't know what that is. You can tell me. So R Thevenin is going to be 27 over 12K. You agree with that, everyone? I don't know what that is.
2.2.
2.what?
2.25.
2.25K ohms. All right. Now I have that. Now I can do the analysis, because here's what we do it the same way we just did it. Now I can come over here. And the only thing I'm going to do is replace those 2 resistors with the Thevenin equivalent circuit. Can everybody see that? So when I'm doing that, now this gets taken out, these 2 get taken out. And now I put that Thevenin equivalent circuit. It's an actual voltage here of plus to minus 2.5 volts. And it's got a resistance here of 2.25 K ohms. Do y'all agree? Remember, this is how you do this kind of problem. Hint, I can't be more clear. This is how you do this kind of problem. You're getting a Thevenin equivalent source for the resistive division. Now, once you have that, can I find my base current here? What would this base current be based on what we just did? Anyone? Well, let me ask you this. How much voltage is available to drive the current around that base circuit? Anyone?
2.5.
It's got 2.5, but less the 0.7, right? Correct? So the voltage that's available is 2.5 minus 0.7. That's the amount of voltage that's available to drive it. But what's stopping it? Well, there's a resistor in the base circuit right off the bat that's 2.25K, correct, class? So that's 2.25K plus, what else is stopping it?
2K.
2K, but what do we have to multiply that by? Beta plus 1, right? Because it's going to be magnified. Everybody with me? So it's that plus beta plus 1, or 201. I would just put 200 times 2K. And you can see right off the bat that this is going to dominate the effects, right? The 201 times 2K, not the 2.25K. So out of curiosity, what do you get for IV? Can somebody help me with that? And I appreciate all the people that bring their calculators and help work these problems for me. I've always encouraged people to do that. It seems to stay with you longer. If you work the problems, it stays with you. Anyway. By the way, there's a senior design fair in this building at the basement this afternoon if you want to go take a look at it. what some of these kids have come up with. I haven't seen them all. I can only imagine that they're not allowed to do rail guns and things like that anymore. I had fun building a rail gun a couple of times. And 9/11 happened. So that's what I ended up building.
Is that 200, is that plus 201 times 2K?
Yeah, it's beta, it's plus 1. Beta's 200, 200 plus 1 is 201, right?
So that's 4.45 micro amps.
Anybody confirm that?
Yeah.
4.1.
1.99.
I got 4.4.
I got the same thing he got.
Remember, it's 2.5 minus,
Times 10 to the
what's,
negative 6.
it's, all right, times 10 to minus 6?
Yeah, that's what I got.
Max,
Yeah.
how many got that? I go with the majority. All right.
That's what I said.
Okay. Hi. Oh, you don't need me.
Just ignore me. I'm sorry.
Don't worry about it. I thought you were the police. Anyway, a lot of criminals. I'm working. All right. Anyway, that's IB, correct? Now what do we do? No, go ahead, stay. You're gonna be talked about, believe me.
I'm sorry. I'm just counting the tables for my final.
Okay. Okay.
Our final is held here, correct?
Yeah, our final's here. And you know what it is?
Monday at 12.
Again, Monday at 12, right? And I've had this happen. I've had a guy show up, no kidding, right after the final is over.
Oh my God.
You know, what do you do? Oh. Oh, God, that was bad. All right, you know, the truth is, it's not the 12 o'clock ones that happens to you. It's the 8 in the morning ones, because the alarm clock just doesn't work when you're that dead. And so they don't get up and they'll miss it, or they'll come in at like 9:30 or 10 in a panic. Please get your sleep. What were you gonna say? Did you have your hand raised, or did you?
You go over how you got the bottom of the IB equation?
Yeah, I'll do it. If you look at this, first, this 2.5 volts is gonna drive current, right? The thing you have to do is always take the VBE off, right? So that's that. But what limits it? Well, that resistance does, right? But this resistance, what happens? Instead of having IB go through it, what actually flows through there? Isn't it beta forward plus 1 times IB that flows through there? So I had multiplied that by 2K, right? The idea is the beta plus 1 times 2K is the effect of that resistance in the base circuit. If you look back what I did, the step right before this, I went through and I summed voltage drops around that closed loop. Do y'all remember this? When I did that, I said an increase of this voltage, which is VBB, minus IB times this resistance, which I called RB, minus this voltage VBE, and then minus this voltage drop. Well, that voltage drop is going to be that resistance, 2K, times the emitter current. And the emitter current is beta forward plus 1 times IB, all right? And that's the reason that beta plus 1 is right there, 201 times 2K, all right? So it amplifies it. In other words, it enhances the value. Yep.
For our Thevenin, for that 27K over 12K, should that be 2.5 ohms instead of 2.5K ohms?
Well, if you look at that, this is K and this is K, right? So if I take 9 times 3, that's 27K squared, right? Divided by 9K plus 3K is 12K. So K squared is by K is just K. All right. Back to this thing, that's IB. What's the next thing we're gonna get? What does IB give you? Yeah. IC. What is IC?
BFIB.
That's gonna be beta forward times IB. Beta forward is 200, right? So just multiply that by 200. So it's gonna be 10 to the minus 4, it's about, what is that, 8.9?
8.91.
Amps, right? Y'all agree with that? Now, if I want, so now I've got my IC. Now, to get this VC, how do I get this right here, guys? That's the voltage between the collector terminal and ground. From here to here. Well, ask yourself this. If this resistor wasn't here, what would it be from here to here? It would be 10 volts, right? So it's 10 volts less this voltage. Y'all see that, class? Because I'm going from here to ground, not across the collector to emitter. So V collector here is going to be 10 minus IC times RC, and I'll put the values in, or V collector here is going to be 10 minus an IC, I'm going to just leave it as IC, times 5,000. So what do you get for that, anyone? That's about 10, that's 8 volts or so, isn't it? Can anybody do that for me? 10 minus that value of IC, well maybe, yeah, I think it's about 8.
I got 5.5.
What'd you get?
5.5. Sorry.
Sorry. 5.4 volts. Guess my math is. Are you with me, everyone? Yes.
Why is the emitter resistance not factored into the VC?
They only want the voltage from here to ground, right?
Right.
They don't want it from collector to emitter.
Okay.
So the only voltage that you have to worry about taking off, you might say, is that.
Okay, I see it.
Okay? All right, now, you all see what I've done there, right? It's not hard if you stay tuned, and I'll give you problems, but I want to make sure everybody's clear on that. You got me? Question for you.
Yeah.
Oh, well, no, now we're going to do another one. I want to do one more.
It's not, it's.
Dr. Fancy, can we take the last 2 minutes and talk about the final instead?
We're going to. Well, you want to do it right now?
Yeah, we only have 10
All right, I can tell you right now what the final is going to be about. See my old test? See the test? All right. That's the way the final is. I go ahead and all the homework I peruse through, and I basically adapt homework problems. Take a look at the tests you just took. What are they? They're homework problems, maybe with different values, right? That's the only thing they are. There's going to be delta Y. I mean, if you want me to get the major topical areas, I assume you know that you have to understand mesh, Thevenin, and nodal. Those are, I mean, you got to understand that, right? So those are analysis techniques. Then you have to understand transients. That's both capacitor resistor and inductor resistor. So you got transients, right? But we've been doing Thevenin, nodal, and mesh all the time, right? Then after that, what happens? Then we get in to both transformers and mutually coupled circuits, correct, class? They're 2 slightly different things, right? So then you have those, and we did a whole bunch of them, if you recall. After that, we go into power, 3-phase power, delta to Y conversions, right? Y to delta. Then we do operational amplifiers. I mean, these are just the major topics. This is not hard to see. After operational amplifiers, you have a diode, and it'll be a simple diode problem. After diodes, you have transistors. That's it. I mean, if you just look at the major themes, that's what they're going to be. I'm not going to ask you anything bizarre. If they ask me how difficult is it, take a look at the last 2 tests. Take a look at the homework. That's the same level of difficulty. You will literally see homework problems modified put on there. And I do this all the time. I will take a homework problem. I may take one and slant some resistors just to throw you. I mean, really, you can figure these things out. You're engineers. But I'm not going to do something diabolical and give you some kind of crazy circuit with 5 or 6 different currents you have to find. You're not going to get more than a 2x2 matrix you have to solve. Just let me finish this thought here. Get your calculators charged. If somebody comes in here and says my calculator's dead, then I'm sorry. All right, I'm giving you fair warning. Make sure it's charged up and working. Make sure you know how to use it for the complex domain for mathematics. You're going to get problems you're going to need to solve the currents for. All right? Yes, sir.
Wondering how many questions are.
That's always one of the things they give me. I don't know how many, but I can tell you there's normally 6 to 8 pages, right? Now, each one of those problems, if you look back at your exam, there are several things I ask regarding that problem. So there might be anywhere from 3 to 4 different things I ask about each particular problem on the page. For instance, in an op-amp, sometimes I just ask for the value of resistance. I could easily ask for the voltage, current. I could ask for several things. For power problems, I asked for current in the main line, voltage across the load, complex powered. I could ask things like this. I don't try to do anything on a final exam that's tricky. It's all based on what we covered. This is a basic class. It's not, you're not an electrical engineer. You're not gonna get probed to see that you're clever enough, all right, in this kind of class. It just is an overview, and it's at a basic level. There's nothing really complicated here. One thing I will tell you though, make sure with your calculators you brush up on the imaginary mathematics of that you can do these things fairly efficiently. The first exam, a lot of people blew it because they weren't familiar with how to use their calculators with complex, in the complex domain. I'll leave it at that. And I mean, there was a lot of bizarre kind of answers that I saw. So make sure you're good at that. I think I'm clear about that. You've done a lot of those problems. Did you have something specific you want to ask or not?
No, I just wanted to know.
Any other questions about the final exam? I figured, yes.
Norton's gonna be on there, or is that kind of absorbed?
Well,
into Stephens?
Thevenin and Norton are kind of the same, aren't they? Yeah, if you know one, you know the other. The Norton's just what? A source transform. You take a Thevenin, turn it into a current source in parallel with resistance, right? Thevenin is when you have a resistance in series with an open circuit voltage. So you're going to have to know source transform. Yes, source transforms are handy, dandy little things to do problems. You did a lot of these problems, right? You know what I'm talking about. They're basic problems. There's nothing crazy, nothing more than two currents you'd ever solve for. So a 2x2 matrix is as big as they get. Most of the problems can be solved very efficiently if you know what you're doing, and quickly too. By the way, on the final exam in this class, I've had people turn it in 25 minutes, 20, and they're completely right, because they really know. And I've had people go 2.5 hours and still maybe maybe two problems aren't even touched. All right, so I get a huge, and when I say huge, I'm not kidding, an enormous spread in the grades. I'll get a whole bunch of 40s out of 40 or whatever, 60 out of 60, 80 out of 80, and I'm going to get people to get 5 out of 8 kind of deal. That's the way it happens. So, and the people that get that, usually the people that don't even bother showing up most of the time, they show up for the final thinking it's a cakewalk, and then all of a sudden, it doesn't happen. If you've been keeping up, you're in good shape. But get your sleep. If you have questions, I got a final on Monday, and I probably got a lot of meetings, but send me an email. I'll try to be in here in the afternoon, like at around 2 o'clock. I'll try, all right? And if I can't, I'll let people know. Now, you did the group me thing, right? I appreciate that. You and who recorded it?
I recorded it. He did the group.
You did the group me? Or who did? You did. Well, I appreciate that. Was that all something you enjoyed?
Yeah.
The recording the lectures I found extremely helpful. Anytime you can collaborate with your fellow friends, the people in the same class, it's really good, especially when the instructor doesn't care what you say about it. I don't care what you say, I'm going to do me what you say. Most of the time I don't even look at it unless somebody says, would you please look at GroupMe? So I don't care, but I'll tell you this much. It is very important that you can learn to network like that in classes this size, because there's some people that really, really they struggle a terrible amount and they need some help. And some just get it like, I mean, I look at the front row, we got people here that are basically 40 out of 40 all the way, they get nothing but straight. Almost. I think you've got them just about the whole thing is perfect, and maybe them too. But then I got other people that, they got 5 other courses, they're in band, who knows what else. They don't have a lot of time and they're struggling, so it helps when you have this as a group meeting or something like this. I'd encourage you to tell your other faculty members and professors that you have in other courses to record the lecture and make it available, and also allow students to collaborate. That's one lesson I've learned in the last 10 years that is especially helpful to students, graduate students even more so than you guys. Because the grad students are the guys that get the problems that pull their hair out. Any other questions? I was going to do one more. You mind if I do one more? Yes. All right, here we go, guys. Last one for the year.
Oh man.
I was here. Where did you start? Take a selfie.
Alright, this is 100 volts, not 10, 100 volts. I want the collector and emitter voltage there, alright? So, how do I do it? Where do I always go? Guys, what am I after first? Base current, right? IB. How do I get IB? Well, I look for the voltage that's trying to drive current around the base circuit. You see, it's the 100 volts, class. Y'all see that? So I take 100. Then what do I subtract from it, class? 0.7 in this case. Almost no difference. What limits the current?
The
So
resistor.
540K. You'll notice there's no emitter resistance, right? So that gives me IB. Once I have IB, what am I gonna get?
I see.
Well, how do I get IC? Class? Beta, right? Times IB, or it's 100 times IB. Agreed? Just leave it as 100 IB. I don't have time, because I'm bad at time. You all with me? Once I have that, now that I have IC, what do? I got IB and IC, two of the three, what do? How do I, well, I don't need IB. What's the next thing? How do I get this? Class?
By subtracting IC times the.
Put 100, that's how much I had, right? All with me? What do I subtract, you're right?
IC times.
IC times RC, whatever that is. Make RC 2,000 ohms. And you can go ahead from there. Now, that's the problem with self-biasing. There's no second source. That's another method to self-bias. Those are the problems that you're gonna get, that kind of problem. Got it, class? All right, if you got more questions, I'll hang out. More power to you. Does somebody need to take a quiz or a test or something? There's at least one person who can show up for the second test.
Do you have any quizzes left over?
Hey, you come up to my office, you wanna see some quizzes? Anybody been up there to try to grab their stuff? It's a nightmare. I got more quizzes up there than I care to. Yeah, come on upstairs.